filling of orbitals atom. That is, the filling of electrons into orbital of different atoms takes place according to the Hoffer principle, so which is based on the Pauli exclusion principle, the Fund's rules of the maximum multiplicity, and the relative energies of the orbital. First, Hoffer principle. Hoffer means, that is German word, that is German mean building up. The building up of the orbitals mean the filling of the orbitals with the electron. The principle states that the ground state of the atom, the orbitals are filled in the order of increasing energy, like this. See, in the electron first occupies the lowest energy level, that is lowest energy orbital available in them, and enter to the higher energy, that is orbitals only after the lower energy orbitals are filled. The order in which the energy is the orbital increasing, and hence the order which orbitals are filled in this follow up. Look at this. This is the order of filling orbital. 1s first, then 2s, 2p, 3s, then 3p, 4s, then 3d. Look at this. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, and 7s, like that, and so on. See, the order may be remembered that using the methods given, that is, look at this, that from the top of the direction to the arrows, look at this, arrows gives the order of filling of the orbital, that starting from the right top of the bottom left. Then the Pauli exclusion principle. Before that, the arrangement of orbital with increasing energy of the basis of n plus L rule. That is, n plus L rule means orbital. For first 1s orbital, n is equal to 1, L is equal to 0. So that n plus 1 rule is 1. 2s, n is equal to 2, L is equal to 0. So that 2. And 3s. 3s, n is equal to 3, L is equal to 0. So that 3 plus, this is n is equal to 2, not 3. N is equal to 2 and L is equal to 1. L is equal to 1. So it will become 3. So here the 2p, that means n is equal to 2, has lower energy than the 3s. Okay, this is 2p, not 3s. This is 2p. So here 2p is n is equal to 2, L is equal to 1, 2 plus 1 is equal to 3. That means 2p has lower energy than the 3s. Now 3s, n is equal to 3, L is equal to 0. So 3 plus 0, 3. Then 3p, n is equal to 3, L is equal to 1, so 4. Here the 3p, n is equal to 3 means has lower energy than the 4s. 4s equal to, n is equal to 4, L is equal to 0, that 4 plus 0, that is 4s is equal to n is equal to 4. 3d, n is equal to 3 and L is equal to 2, 3 plus 2, 5. So 3d has lower energy than the 4p. Then look at 4p, n is equal to 4 and the L value is equal to 1. 4 plus 1 is equal to 5. So 4p is equal to n is equal to 4. Here the next is the Pauli exclusion principle. The Pauli exclusion principle, the number of electrons that are filled in the various orbitals is restricted by the exclusion principle, that is given by Wolfgang Pauli. According to the principle, no two electrons in an atom can have the same set of 4 quantum numbers. I repeat that, no two electrons in an atom can have the same set of 4 quantum numbers. The Pauli exclusion principle statement is only 2 electrons may exist in the same orbital, and these electrons must have opposite spin. So this means that 2 electrons can have the same value of 3 quantum numbers, that is n, L and ml. Principal, azimuthal and magnetic quantum number, but must have the opposite spin quantum number. The restriction imposed by Pauli exclusion principle on the number of electron in an orbital helps in calculating the capacity of the element to be present in the subcell. So for example, subcell is 1s comprises of the one orbital, and the maximum number of electrons present in the 1s subshell can be 2. That's mean 1s. So the subcell having maximum of electron is 2, that having opposite spin. So that is in p orbital. This is for s orbital. P orbital means 3 subcells. So the maximum of electron possibility is 6. D 5 subcells are there. So maximum of electron 10. And F 14, because of 7 subcells are there. 1 2 3 4 5 6 7. So 7 subcells are there. So that the maximum number of electron can be 6 in p orbital, d in 10 in d orbital, f in 14 in the f orbital. So this can be summed up in the maximum number of electron in the subcell with principal quantum number n is equal to 2n square. This is called Pauli exclusion principle. Next is the Fund's rule. The Fund's rules of the maximum multiplicity. Here this rules deals with the filling of electron into the orbitals belonging to the same subcell. That is the orbitals of the equal energy called a degenerate orbital. The statement of the Fund's rule is pairing of electron in the orbital belongs to the same subcell, that is p, d or f, do not take place until each orbital belonging to that subcell has got 1 electron each, that is it's singly occupied. So like this, first one filling like this, then pairing up like this. So since there are 3 p orbitals, 3p, 5d and 7 orbitals, therefore the pairing of electron will stop starting the p, d and f orbital with the entry of 4th, 6th and the 8th electron, like this. The 4th electron enter like this. First 3 electrons, the 3 electrons 1 2, suppose 4 electrons in p orbitals mean you have to write 1 2 3 then 4, not like that. Suppose 4 electrons means you are not allowed to write like this. See, the first electrons are filled one by one, next subcell, then pairing off like this. In d orbital, the similar way you have to follow. 1 2 3 4 5 6. The 6th electron start off filling the first subcell, 7th electron here, 8th electron here, like this. So here the same there are, that's mean it has been observed that the half filled and fully filled degenerate set of orbitals acquire extra stability due to their symmetry. Then the electronic configuration of atom. Electronic configuration of atom, that is the distribution of electron in the orbitals of an atom, is called electronic configuration. That is the distribution of the electron. If one keeps in mind the basic rule which govern the filling of different atomic orbitals, the electronic configuration of different atom can be written very easily. That is, the electronic configuration of different atoms can be represented the way, that is S P D, that is SA, SB, S power C, up to that notation. Then the orbital diagram. Orbital diagram is S orbital 1 subshell, P orbital 3 subshell, D orbital 5 subshell, F orbital 7 subshells, like this. So 7 subshells are there. In the first notation, the subshell is represented. Look at this. Subshell is represented by the respective letter symbol and the number of electrons present in the subshell is depicted. So here the superscript like A, B, C, etc. The similar subshells represented for different subshells, so different cell in the differentiated by writing the principal quantum number before the respective subshell. So in the second section, that is the second notation, each orbital have the subshell is represented by the box and the electron represented by an arrow. That is, you can write like this, the arrow, the positive spin, and the down arrow, that does indicate negative spin. So the advantage of the second notation over the first is the represent all four quantum numbers. So for example, the hydrogen atom has only one electron because the hydrogen atomic number is 1. So the s orbital only one subshell. So you have to write like this. So this is for oneness. For an helium atom, atomic number is 2. So this is also s orbitals only. So one is spin, another one is opposite spin. So this is oneness. So you have to write the electronic configuration for hydrogen is 1s1. For helium, 1s2. The superscript indicates that A, B, C like this. So that the numbers, that is the atomic numbers. The third electron, that is in lithium, look at this. Lithium is not allowed to in the first 1s orbital because of the Pauli exclusion principle. It therefore takes place next available choice, that is namely 2s orbital. The electronic configuration of lithium will be, look at this, lithium atomic number is 3, so that 1s2, 2s1. So the next orbital is 2s orbital. So that next electrons enter into the 2s orbital. You have to write like this, 1s2, then 2s1. Then beryllium atomic number is 4, 1s2, 2s, so 2s2. Here also same, 1s, then 2s. Boron 5, the atomic number is 5, so 1s2, 2s2. Next available orbital is what? 2p. So that 2p, remaining 1 electrons are there, so that 2p 1. So 1, 2, 1, 2, 1. The p orbitals entering the first electron is boron atom. Carbon 1s2, 2s2, 2p 2. Now count this 6. Again write 1s orbital 2 electron, 2s orbital 2 electron, and 2p orbital having 2 electron. Then N, nitrogen atomic number is 7, so 1s2, 2s2, 2p 3. 1, 2, 3, 4, 5, 6, 7. So nitrogen having a half filled p orbital. Then oxygen is 8, 1s2, 2s2, 2p 4. So oxygen having filling like this, 1s 2 electron, 2s 2 electron, 2p 1, 2, 3, then fourth electrons enter here. Then fluorine 9, so 1s2, 2s2, 2p 5. So 1s 2 electron, 2s 2 electron, remaining 5 electron you have to write like this, 1, 2, 3, 4 and 5. Then neon 1s2, 2s2, 2p 6. So all p orbitals electrons are completely filled. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the follow-up. This process is complete with the neon atom. So the orbital pictures of the element like this. Then the electronic configuration of the elements. Here the sodium. The next neon, next is what? Sodium. What is the atomic number here? Sodium atomic number is 11. Here the sodium atomic number 11. The electronic configuration will be 1s2, 2s2, 2p6, 3s1. The third, the 3s1, and the argon 1s2, 2s2, 2p6, 3s2, 3p6. See, follows the exactly same pattern as the element from lithium to neon, with the difference that the 3s and the 3p orbital. Only the difference here, there is 2s, 2p, here 3s, 3p orbitals are getting filled now. This process can be simplified if we represent the total number of electrons in the first two cells by the name of the element neon. Look at here, the neon is what? 10. Atomic number is 10. So 1s2, 2s2, 2p6. Up to this indicates what? Neon. So that we can write it up to this neon. So that you can write it neon, then 3s1. This indicates the electronic configuration of the sodium atom. So the electronic configuration elements from the sodium or argon can be written as like this, or you can write for argon, this is up to argon is 18. So you can write it this simply argon. Suppose the next element means potassium, or you can write like this. For example, potassium, you can write it 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Here the 4s1, you can write it the argon 4s1, the potassium electronic configuration, right? So this is called a valence cell electronic configuration or outer electronic configuration. This means the electrons are completely filled in cells are known as the core electrons, and the electrons that are added in the electronic cell with the highest principal quantum numbers are called valence electron. Here the valence electron, the neon are the core electrons of the electron, the sodium to argon, the valence electron, the potassium, look at this, and the calcium in 4s orbital being lower energy than the 3d orbitals, the occupied by the 1 and 2 electrons respectively. So calcium the similar way like this. So for example, calcium atomic number is 20, you can write it argon 4s2. So this is the electronic configuration. This is the valence, the 4s2 is the valence electronic configuration. In a new pattern followed beginning with the scandium, that is in 3d orbitals being lower energy than the 4b orbital. Already we know that. So it is filled first. Consequently, in the next 10 elements, scandium to copper, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc, not copper, zinc. So the 5 3d orbitals are progressively occupied. So we may puzzled by the fact in the chromium and copper. Here, look at here, scandium to zinc, the electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1. Look at here, the copper, chromium and the manganese. I will write the outer electronic configuration. There is 3d1, 4s2, 3d2, 4s2, 3d3, 4s2, for chromium 3d5, 4s1, manganese 3d5, 4s2, 3d6, 4s1, 3d7, 4s2, 3d8, 4s2, 3d10, 4s2, 4s1, 3d10, 4s1. Look at the copper, zinc, chromium and manganese. All this is the exception of this rule. Look at this. First the higher energy filled, then the lower energy electrons are filled because of the stability of the compound. See, we may puzzled by the fact that the chromium and the copper have 5 and 10 electrons. Look at this, 10 and 5 electrons, chromium and the copper. Look at this copper and the chromium. Here the 3d orbital, that is the 3d orbital rather than the 4 and the 9, their position would have the indicate with the 2 electrons in the 4s orbital. Look at this, the 4s orbital. This reason the fully filled orbitals and half filled orbitals have extra stability. That means this is half filled and this is full filled. So they attain the extra stability. That's why P3, P6, D5, D10, F7, F14, etc. So the configuration which are either half filled or full filled are most stable. Chromium and copper therefore adopt chromium, look at this 3D5, adopt this copper 3D10. So configuration, that is with the saturation of the 3D orbital, the filling of the 4f orbital start at gallium and is complete at krypton. In the next 18 elements from rubidium to xenon, the pattern filling 5s, 4d and 5p orbitals are similar to that the 4s, 3d and 4p orbitals are. Okay, so then there is 6s orbital, that is in cesium to barium, cesium and the barium, these orbitals contain 1 and 2 electrons respectively. That's mean then therefore the lanthanum to mercury, the filling of electrons takes place in the 4f and 5d orbitals. After this, the filling of the 6p and the 7s are finally 5f and 6d orbitals takes place. The elements after uranium are all short living and all of them produced artificially. So the electronic configuration of the known elements are that is in your textbook table number 2.6 you can check it. The electronic configuration of the all elements are given there. Then the stability of completely filled half filled subshell. The ground state electronic configuration of atom elements always correspond to the state of the lowest total electronic energy. So the electronic configuration of most atoms as follows the basic rules already we were seen. There is in certain elements such as copper or chromium where the two subcells 4s and the 3d differ slightly their energy for copper and the chromium. Chromium atomic number is 24, so that 3d 5, 4s 1. Copper 29, 3d 10, 4s 1. See, first here the higher energies are filled. In the certain elements like copper and chromium, two subcells are differ slightly in their energy of electrons shift from the subcells of lower energy, that is in 4s, to the subcells of the higher energy, that is in 3d. So provided such a shift, the result is all orbitals of the subcells of higher energy getting either completely filled or half filled. This is completely filled, this is half filled. So the valence electronic configuration of the chromium and the copper like this 3d10, 4s1 for copper, chromium 3d5, 4s1. It has been found that the extra stability of associated with the electronic configuration. Look at this extra stability, the cause of stability of completely filled and the half filled. Here this reason that why like this mean the symmetrical distribution of the electron. It is known as the symmetry leads to stability. The completely filled or half filled subcell have symmetrical distribution of electron in them and are therefore the more stable. The electrons in the same subcell, here the 3d have equal energy, but look at this 3d, they have a equal energy but different spatial distribution. Consequently, their shielding of one another is relatively small and the electrons are more strongly attracted by the nucleus. Look at this, the first, the electron, the 4 exchange by 1 electron. 4 exchange by electron 1. Then look at this 2, that is 3 exchange by 2. Then look at this 2 exchange by 1, sorry 3 exchange by 3 electron. Then 1, look at this 1 exchange by 4 electron. So here the exchange energy, the stabilizing effect arises whenever 2 or more electrons with the same spin are present the degenerate orbitals of the subcell. So these electrons tend to the exchange their position and their energy released due to the exchange is called exchange energy. The number of exchange that can takes place the maximum when the subcell is either half filled or completely filled. This half filled and the completely filled electron, that is the stability. You may note that the exchange of energy on the basis of the Hund's rule that electrons which enter orbitals in equal energy have the parallel spin as far as the possible. So in other words, the extra stability of half filled and completely filled substance due to the relatively small shielding, smaller Coulombic repulsion energy, larger exchange energy. So the details and the about the exchange will be dealt with the higher class. That is, you can learn in the higher classes. Thank you, student.